Good evening, I am Preeti from BSc Chemistry on our second year. Chapter Non-Aqueous Solvents. Most of the chemical reactions are carried out in solutions, and the behavior of substances also depends upon the nature of the solvent. In the earlier days of development of chemistry, the reactions have been carried out only in one solvent, namely water. It has been facilitated by its ready availability, ease of purification, together with its favorable physical and chemical properties such as long liquid range 0 to 100 degrees Celsius, high dielectric constant, specific heat, high heat of volatilization, dipole moment, etc. Water is neutral, odorless, non-toxic and non-poisonous. It can therefore be handled safely. The properties of water make it an excellent and useful solvent for a large variety of substances. In fact, the excellent properties of water have hindered the development of non-aqueous solvents, the solvent other than water which are used for carrying out chemical reactions are called non-aqueous solvents. Attempts have been made to find some other substances which could behave as good solvents like water. Organic chemists have been using many solvents such as benzene, carbon tetrachloride, acetone, ether, etc. for dissolving organic compounds which are insoluble in water. Now there are many other solvents available, for example, liquid NH3, H2SO4, liquid HF, liquid sulfur dioxide, etc., which have been frequently used. In the present unit, we shall discuss briefly the important features of non-aqueous solvents such as NH3 and SO2, physical properties of solvents and their role in chemical reactions. The usefulness of a solvent is determined from its some specific properties that may help to carry out the chemical reactions and separate the product more conveniently. Some of the important physical properties of the solvent are discussed below. First, melting point and boiling point liquid range. The melting and boiling point of a solvent determine the temperature range within which the solvent can exist in the liquid state under atmospheric pressure. Since most of the reaction in a solvent system are carried out in liquid phase, the melting point and boiling point give the temperature range within that solvent is useful. The melting and boiling point for some common solvents are given in table. In this table, melting point and boiling point of some common solvents are given below. For example, H2O melting point 0 and boiling point 100 degrees Celsius, and the NH3 minus 77.7 degrees Celsius is the melting point, and minus 33.4 is the boiling point. And the next is SO2. Its melting point is minus 75.5 degrees Celsius and boiling point is 10 minus 10.2 degrees Celsius. It is clear from the above table that water has excellent liquid range from 0 to 100 degrees Celsius at ordinary temperature and pressure. Acetic acid can also act as solvent at ordinary temperatures, while NH3 and SO2 can act as solvents only at low temperatures. Heat of fusion and heat of vaporization. The second point is heat of fusion and heat of vaporization. The values of heat of fusion and heat of vaporization help to know the nature and strength of forces which hold the molecules of the solvent together in the solid or liquid state. As we know, the amount of heat absorbed by 1 mole of the substance to change from solid to liquid state is called its molar heat of fusion. Similarly, the heat absorbed by 1 mole of the substance to change from liquid to vapor state is called its molar heat of vaporization. Large the value of heat of fusion or heat of vaporization, the stronger are the intermolecular binding force in the solid or liquid respectively. Therefore, the magnitude of molar heat of fusion and molar heat of vaporization give us some insight into the magnitude of molar heat of fusion and molar heat of vaporization, into the nature and strength of intermolecular force, and these also determine the solvent properties. A better idea of the intermolecular forces in a solvent is obtained by the ratio of molar heat of vaporization to the boiling point. This ratio is called Thornton constant. Thornton constant is equal to delta H evaporation divided by TB. For normal liquid, if molar heat of vaporization are expressed in Cal and boiling point in absolute scale, then the Thornton constant has the value 21.5. Such liquid exist as independent molecule without any bonds between them. A higher value of Thornton constant indicate associated molecules. For example, common solvents like water, ammonia, hydrogen fluoride, and Thornton constant value greater than 21.5 and are therefore associated liquid. The molecules of these liquids are polar. The association of polar molecules is due to their tendency to orient themselves so that the oppositively charged ends of the molecules come near to each other. Third point is dielectric constant. This property is a measure of the polar nature of the solvent and help us to estimate the solubility of polar or non-polar substance in the solvent. According to Coulombic law, the force of attraction between two charged ions is given by F is equal to Q plus into Q minus divided by epsilon naught R square, where Q plus and Q minus are the charges of the cation and anion respectively. R is the distance between them. Epsilon naught is a constant called dielectric constant of the solvent. If epsilon naught is large, the force F will be small. As a result, only a small amount of energy will be required to separate the ions, and it will be easy to dissolve an ionic substance. Thus, in solvents of high dielectric constant, the ionic substance will dissolve readily. With the decrease in dielectric constant, the solubility of ionic compounds will decrease. It is clear that solvent like HF and H2O are good solvent for ionic and polar compounds because of their high dielectric constant values. On the other hand, solvent like NH3, SO2 with small values of dielectric constant show decreased tendency to dissolve ionic compounds, and especially those containing multi-charged ions. For example, carbonates, sulfates, phosphates, and particularly insoluble in liquid ammonia or liquid sulfur dioxide. The next point is dipole moment. The dipole moment is related to the dielectric constant of the solvent. An ionizing solvent has large dipole moment and also has a large dielectric constant. It is related to the polarity of the bond in the molecule. Greater the polarity of the bond in the molecule, larger is its dipole moment. Solvents having high dipole moment have greater tendency to dissolve the polar or ionic substances. This is because of the fact that the greater polarity result in strong bond between the solvent and the solute molecules, and large solvation energy is released. This large solvation energy is sufficient to overcome the lattice energy in the solute molecules and help in dissolving the solute. The next point is viscosity. It is a measure of the fluidity of the solvent. Solvents like water, ethyl alcohol, and carbon tetrachloride have low viscosities and are highly fluid and flow rapidly under ordinary temperatures. On the other hand, anhydrous sulfuric acid and high molecular weight of hydrocarbons have high viscosities and flow at much lower rates at ordinary conditions. In solvents of low viscosities, the operations such as precipitation, crystallization, filtration, etc., can be easily carried out without any difficulty. With increasing the viscosity of a liquid, increases the difficulty of such operations. Type of solvents. Non-aqueous solvents have been classified into many ways. The following are the important classification based upon the chemical properties of the solvent: protonic and non-protonic solvent, acidic and basic or amphiprotic solvent, ionizing and non-ionizing solvent, coordinating and non-coordinating solvents, protonic and non-protonic solvent. The solvent from which protons can be derived are called protonic solvents. Protonic solvents contain ionizable hydrogen ion. Common examples are H2O, HF, H2SO4. The solvent from which protons cannot be ordinarily derived are called non-protonic solvents. These are also called aprotic solvent. In other words, these solvents do not contain ionizable hydrogen atom. Common examples are liquid SO2, N2O4, C6H6, CCl4. acidic, basic, and amphiprotic solvents. Their classification is based upon the acidic or basic behavior of solvent. The solvent which have a strong tendency to donate protons are acidic in nature and are called acidic solvent or protogenic solvent. For example, H2SO4, liquid hydrogen fluoride, HF. Solvent which have strong tendency to accept protons and are basic in nature are called basic or protophilic solvent. For example, liquid ammonia, pyridine, hydrazine. The solvent which neither have a strong tendency to gain nor a strong tendency to lose protons are called amphiprotic and amphoteric solvents. In other words, they neither behave as a strong acid nor behave basic, but can behave as acidic as well as basic depending upon the nature of the reacting species. For example, water, ethyl alcohol, methyl alcohol, etc. The third point is ionizing and non-ionizing solvents. The solvent which are capable of undergoing self-ionization or auto-ionization are called ionizing solvents. Some common examples like H2O, NH3, etc. These ionize as shown below. H2O plus H2O give us the equilibrium reaction H3O positive plus OH negative. These solvents are generally polar or ionic in nature. On the other hand, the solvents which do not ionize at all are non-ionizing solvents. Some common examples are benzene, carbon tetrachloride, hydrocarbons, etc. These are non-polar or non-ionic in nature. The fourth point is coordinating and non-coordinating solvents. The solvents which are capable of coordinating with the metal ions or anions of the solute are called coordinating solvents. For example, NH3, SO2, dimethyl sulfoxide, etc. On the other hand, the solvents which are not capable of coordinating with the metal ions or anions of solute are called non-coordinating solvent. For example, CCl4, saturated hydrocarbons, etc. These are not of much interest to inorganic chemists. Type of reactions in non-aqueous solvents. First is metathetical or precipitation reaction. The reaction in which precipitation occurs on mixing two solutions are called metathetical or precipitation reactions. These type of reaction can be predicted if the values of the solubility products of the compounds formed in the solvent are known. These values depend upon the nature of the solvent used. For example, in water, silver nitrate and barium chloride react to give a precipitate of silver chloride, leaving barium nitrate in the solution. On the other hand, liquid ammonia, a precipitate of silver chloride, combines with barium nitrate to give precipitate of barium chloride, leaving silver nitrate in the solution. Therefore, reversal of a chemical reaction takes place on changing the solvent. Similarly, sodium hydroxide is highly soluble in water, but it can be precipitated in liquid ammonia. Water soluble copper sulfate may be precipitated in anhydrous acetic acid. And the next point is salt formation. The reactions between appropriate acidic and basic substances to form salt are called salt formation reaction. In such cases, the solvent used must be one in which the appropriate acid and base can exist. For example, sodium uride and cannot be prepared by the reaction of urea on sodium hydroxide in water. It is because the strong base available in water, the OH negative ion, will not take a proton from urea molecule. In other words, the sodium salt of urea is unstable in water and uride ion will take a proton from water to form hydroxide ion. However, this salt can be easily formed in liquid ammonia solution by the reaction of urea with strong base sodamide. The third point is acid-base reaction. The acid-base reaction in non-aqueous solvent can be explained on the basis of solvent system concept. As already learnt, according to the solvent system concept, an acid is a substance that by direct dissociation or reaction with the solvent gives the cation characteristic of the solvent. Similarly, a base is a substance that gives the anion characteristic of the solvent. The acid-base behavior of a substance depends upon the acid-base nature of the solvent, the character of the solute, and the solute-solvent interaction. In case of protonic solvent, cation is the solvated proton and the Bronsted protonic concept is same as the solvent system concept. For example, in liquid ammonia solvent, NH4 positive ions act as acid and NH2 negative ions act as base. The neutralization reaction occurs. In non-protonic solvents such as benzene, carbon tetrachloride, Lewis acid base type of reaction can occur because of non-ionization of the solvent. The acid-base behavior of a solute in a solvent depends upon the acidity or the basicity of the solvent. For example, acetic acid behaves as strong acid in ammonia, weak acid in water, but base in. Fourth point is solvolytic reaction or solvolysis. The reaction in which the solvent molecules react with the solute in such a way that the solvent molecules split up into two parts, one or both of which get attached to the solute molecules or ion are called solvolytic reactions. Since these reactions occur through self-ionization of the solvent, the concentration of either the cation or the anion is changed. For example, the solvolytic reactions in water, ammonia, and ethanol are given as below. Water as solvent. 2H2O gives the equilibrium reaction H3O positive plus OH negative. SO2Cl2 plus 4H2O, the equilibrium SO2 OH2 plus 2H3O plus 2Cl negative. It may be noted that in case of solvent like water, ammonia, alcohol, acetic acid, etc., the terms hydrolysis, ammonolysis, alcoholysis, and acetylysis are used respectively. The fifth point is solvation. The reaction in which the molecules of the solvent get attached to a solute species, cation, anion, or molecule are called solvation reaction. The species formed is called solvate. The solvation reaction in water, ammonia, alcohol, etc. are called hydration, ammoniation, alcoholation, etc. And the resulting solvates are called hydrates, ammoniates, and alcoholates, etc. For example, CuSO4 plus 4NH3 gives us CuSO4.4NH3 ammoniate formed. Solvation of a cation occurs through ion dipole interaction between the positive cation and the negative end of the dipole, or through coordinate bond in which the solvent molecule donates a pair of electrons to the cation. On the other hand, solvation of an ion occurs through ion dipole interaction between the negative ion and the positive end of the solvent dipole, or through hydrogen bonding in case of solvents such as water, ammonia, or hydrogen fluoride. It may be noted that in certain cases it is difficult to distinguish between solvation and solvolysis, because in many solvolytic reactions the first step consists of solvation reaction. However, the term solvation is used for those reactions in which the solvent molecules remain in the resulting product. Let us discuss some reactions in two common non-aqueous solvents. Liquid ammonia. Liquid ammonia is one of the most extensively studied non-aqueous solvent. It is now used as a highly useful solvent and a reaction medium for many types of organic and inorganic synthesis. Its most of the physical properties resemble those of water and given in the following table. Physical properties of ammonia and water. Physical properties of ammonia and water. Freezing point. Water is 0 degrees Celsius and ammonia is minus 77.7 degrees Celsius. And the boiling point. Water is 100 degrees Celsius and ammonia is minus 33.38 degrees Celsius. Density 1, and the ammonia is 0.68 gram per centimeter cube. Comparison of properties of liquid ammonia and water. The comparison of properties of liquid ammonia and water reveals the following points. First is liquid range. The melting and boiling point of liquid ammonia are lower than those of the water. In liquid ammonia, the liquid range is from minus 77 to minus 33 degrees Celsius, and therefore it presents some handling problems. And therefore, some precautions have to be taken while using liquid ammonia as a solvent. It is generally handled in cooled vessels, and nowadays a wide range of techniques have been advanced for handling it. The second point is hydrogen bonding. Like water, liquid ammonia is an associated solvent through hydrogen bonding because it contains a strongly electronegative element, nitrogen. However, ammonia molecules are less strongly associated because nitrogen is less electronegative than oxygen, and therefore NH bond is weaker than OH bond. As a result, the freezing point and boiling point of ammonia are less. Since ammonia is less associated than water, it is a better solvent for organic compounds. The third point is dielectric constant. Dielectric constant of ammonia is lower as compared to water, suggesting it lesser tendency to dissolve ionic compounds. Liquid ammonia is therefore a poor solvent for ionic substance. Soluble salt include most ammonium salt, nitrate, thiocyanate, and iodides. Fluorides and many oxysalt are generally insoluble. However, ammonia has lower viscosity than water and thus might be expected to promote greater ionic mobilities and thereby compensate to some extent for the effect of the dielectric constant. The next point is self ionization. Both ammonia and water show comparable self ionization. 2NH3 gives us NH4 positive ammonium ion plus NH2 negative amide ion, and 2H2O gives us H3A positive hydronium ion plus OH negative hydroxyl ion. However, the extent of autoionization of liquid ammonia is less than that of water. This is clear from its low specific conductance and lower ionic product. KNH3 is equal to NH4 positive and NH4 negative is 1.9 into 10 raised to the power minus 23 at minus 50 degrees Celsius, and KH2O is equal to H3 positive and in OH negative is equal to 1 into 10 raised to the power minus 14 at 25 degrees Celsius. Therefore, ammonia can conduct electricity to a feeble extent. Ammonia is a better solvent than water. The following properties of ammonia make it a better solvent than water. First is liquid ammonia is a very poor conductor of electricity. Second, the specific heat of ammonia is more than that of water. Third, liquid ammonia is less viscous than water. More salt when dissolved in liquid ammonia conduct electric current better than in water. This is not due to ionizing power of ammonia but due to the low viscosity, which greatly increases the mobility of the ions. And the fourth, liquid ammonia has high critical temperature and pressure. Fifth, it is less associated than water and therefore it is a better solvent for organic compounds. Sixth, liquid ammonia forms strong reducing metal ammonia solution with alkali metals, therefore it is an excellent solvent for many reduction reactions. Reaction in liquid ammonia. As mentioned earlier, ammonia has water-like properties as a solvent. It is therefore expected that the reactions which take place in aqueous solution can also occur in ammonia solutions. Some important reactions occurring in liquid ammonia are given below. First is acid-base reaction. The acid-base reaction in liquid ammonia can easily understood by comparing the reactions in water. 2H2O gives us H3 positive and OH negative. According to the solvent system concept of acid and base, the substance producing H3 positive ion in water act as acid while those producing OH negative ions as base. Liquid ammonia ionize as 2NH3 gives us NH4 positive plus NH2 negative. Therefore, the substances producing ammonium ions NH4 plus in liquid ammonia behave as acid while those producing amide ion NH2 negative behave as bases. For example, ammonium salts such as ammonium halide, thiocyanate, nitrate are soluble in liquid ammonia behave as acid. NH4Cl gives us in presence of liquid NH3 NH4 positive plus Cl negative ion. Similarly, amides and imides and nitrides behave as bases in liquid NH3. The commonest base in liquid ammonia is potassium amide KNH2, which ionize as KNH2 in the presence of liquid NH3 gives us K positive plus NH2 negative. Lithium amide, sodium amide, and alkaline earth metal amide have very low solubility and therefore KNH2 is the commonest base in liquid NH3. Protolysis. Certain compound like urea, acetamide, sulfamide, etc., which are incapable of donating proton to water, can readily donate proton to NH3 in liquid ammonia. These reactions are called protolysis reaction. Hence, these compounds act as acid in liquid ammonia. C double bond O NH2 and NH2 plus NH3 gives us CNH double bond O NH2 plus NH4 positive. Sulfamide acid behaving as dibasic in liquid ammonia behave as a monobasic in aqueous solution because NH2 group cannot donate a proton to water. Sulfamide acid behaving as monobasic in aqueous solution. Acid base neutralization. In aqueous solution, the process of neutralization of a strong acid and a strong base involves the combination of H3 positive and OH negative to form practically unionized water. For example, the neutralization of hydrochloric acid and sodium hydroxide may be expressed as HCl plus NaOH gives us NaCl plus H2O. H3O positive plus OH negative gives us 2H2O. In a similar way, the neutralization of an acid and a base in liquid ammonia involves the combination of NH4 positive ion and NH2 negative ion. NH4Cl plus KNH2 gives us, in the presence of liquid ammonia, KCl plus 2NH3. NH4 positive plus NH2 negative in the presence of liquid ammonia gives us 2NH3. There are many examples of amphoteric behavior in liquid ammonia. The compounds that dissolve both in acid and base are called amphoteric substances. For example, in liquid ammonia, zinc amide shows amphoteric behavior analogous to that of zinc hydroxide in aqueous solution. As a base, ZnNH2 twice plus 2NH4Cl gives us in the presence of liquid NH3 ZnCl2 plus 4NH3. As an acid, ZnNH2 twice acid plus 2KNH2 base in presence of liquid ammonia gives us K2ZnNH2 4. Thus, acid gives NH4 positive ions and base gives NH2 negative ions in liquid ammonia. These are termed as ammono acid and ammono base. Reaction of ammono acids. Ammono acid is a substance that furnishes NH4 positive ion in liquid ammonia. Ammonium halide nitrate or thiocyanate are very soluble in liquid ammonia, giving NH4 positive ions, and their concentrated solution act as ammono acids. We know that acid give hydrogen with metal in aqueous solution. In a similar way, the ammono acid solution of ammonium salt in liquid NH3 react with alkali and other metal to give hydrogen. 2Na plus 2NH4Cl gives us, in presence of liquid ammonia, 2NaCl plus 2NH3H2. A saturated solution of ammonium nitrate in ammonia also dissolve many metal oxides similar to their behavior in aqueous acids. For example, Na2O plus 2NH4Cl in the presence of liquid ammonia, 2NaCl plus 2NH3 plus H2O. Solution of ammonium halide in liquid ammonia may be used as acid in the preparation of silane and arsine. For example, Mg2Si plus NH4Br in the presence of liquid ammonia, SiH4 silane plus 2MgBr2 plus 4NH3. Reaction of ammono bases. Ammono base is a substance which in liquid ammonia solution gives NH2 negative ion. The commonest base is potassium amide, which is much more soluble than lithium sodium amide. Metal salt react with ammono base to give amide emits anhydrides which get precipitated in liquid ammonia. For example, AgNO3 plus KHNO2 in the presence of liquid ammonia gives us KNO3 plus AgNH2 silver amide. The second reaction is precipitation reaction. Precipitation reaction involves double decomposition because of the differences in the solubilities of various substances in water and in liquid ammonia. A large number of precipitation reactions which are not normally possible in water have been reported to occur in liquid ammonia. For example, silver silver chloride is precipitated in aqueous solution as KCl plus AgNO3 gives us AgCl and plus KNO3. Similarly, a white precipitate of BaCl2 is produced when solution of silver chloride and barium nitrate in liquid ammonia are brought together. 2AgCl plus BaNO3 twice gives us, in the presence of liquid ammonia, BaCl2 and 2AgNO3. Lithium chloride may be precipitated by the reaction of ammonium chloride and lithium nitrate in liquid ammonia. Iodide and bromide get precipitated when solution of various nitrate and ammonium halides in liquid ammonia are mixed together. Many metal sulfide can be precipitated in liquid ammonia by ammonium sulfide from the nitrate solution of the metals. For example, NH42S plus 2AgNO3 in the presence of liquid ammonia gives us Ag2S, gives precipitate plus 2NH4NO3. The third is ammonolysis. The solubilisis reaction in liquid ammonia are called ammonolysis or ammonolytic reaction. These are analogous to hydrolysis reaction and involve the attachment of ammonium NH4 positive ion or amide NH2 negative ion to the reactant. For example, hydrolysis of SiCl4 occurs as SiCl4 plus 4H2O gives us SiOH4 silicic acid. Similarly, ammonolysis of SiCl4 may be written as SiCl4 plus 8NH3 gives us SiNH24 plus 4NH4 positive plus 4Cl negative. It may be noted that in ammonolysis, an atom or ion from a substance is replaced by a nitrogen containing ion or radical. Some ammonolysis reactions ClSO2Cl plus 4NH3 gives us SO2NH2 NH2 sulfamide plus 2NH4Cl. HgCl2 gives us liquid in the presence of liquid ammonia HgNH2Cl. CCl4 in the presence of liquid NH3 gives us CnHNH2 cut twice. GeI4 in the presence of liquid ammonia GeNH twice. BCl3 in the presence of liquid ammonia BNH2 cut thrice. And the next is PCl3 in the presence of liquid ammonia PNH2 cut thrice. C2H5COOCH3 plus NH3 gives us C2H5CONH2 plus CH3OH. In excess of liquid ammonia, the ammonolysis of TiCl4 occurs in step as TiCl4 in presence of liquid ammonia TiCl3NH2 and further TiCl2NH2 cut twice and further TiClNH2 cut thrice and the next is TiNH2 4. When organic halide which undergo slow ammonolysis are ammonolyzed at the boiling point of liquid ammonia, a mixture of primary, secondary and tertiary amines are obtained. Rx plus 2NH3 gives us RNH2 plus NH4X. Secondary is obtained when Rx plus RNH2 plus NH3 gives us R2NH plus NH4X. The tertiary is Rx plus R2NH plus NH3 gives us R3N plus NH4X, where X is equal to chlorine, bromine, iodine or fluorine. Though ammonia molecule is basic and has a strong tendency to accept proton and therefore it will act as a base. However, toward very strong base, it act as a proton donor. Example of this type of ammonolysis reaction are NaH plus NH3 gives us NaNH2 plus H2. NaCH3 plus NH3 gives us NaNH2 plus CH4. Na2O plus 2NH3 gives us 2NaNH2 plus H2O. Next, fourth point is complex formation reaction. Many complex formation reaction in liquid ammonia are reported which are similar to reaction occurring in the aqueous system. For example, zinc nitrate react with potassium amide to form insoluble zinc amide which dissolve in excess of amide due to formation of complex compound of zinc. ZnNO3 twice plus 2KNH2 in the presence of liquid ammonia. ZnNH3 twice insoluble which is and plus 2KNO3. This reaction is analogous to reaction of zinc nitrate with sodium hydroxide in water. ZnNO3 twice plus 2 NaOH H2O. ZnOH twice plus 2 NaNO3. Some other complex reaction in liquid ammonia. CuCl2 plus 4NH3 in the presence of liquid ammonia give us the complex CuNH3 NH3 4 Cl2. Fifth point is formation of ammoniates. Just as water form hydrates, ammonia also form ammoniates with many inorganic salt. In this compound, the ammonia molecule are coordinated to the cation. Some typical ammoniates are BF3 plus NH3 gives us in the presence of liquid ammonia BF3.NH3. MgI2 plus 6 NH3 gives us in the presence of liquid ammonia MgI2.6 NH3. The sixth point is redox reaction. Liquid ammonia acts as an excellent medium for redox reaction. In liquid ammonia, the oxidizing action of strong oxidizing agent is weaker than in water solution. For example, HNO3 in liquid ammonia does not act as an oxidizing agent. Similarly, KMNO4 in liquid ammonia acts as a very weak oxidizing agent. On the other hand, Reducing agents show increased reactivity. For example, alkali metal act as a very powerful reducing agent in liquid ammonia. For example, sodium metal in liquid ammonia reduce CuI to Cu and KMnO4 to K to MnO4, etc. CuI plus Na gives us in the presence of liquid ammonia Cu plus NaI. The seventh point is solution in liquid ammonia. The dielectric constant of liquid ammonia is low, therefore it is expected to be poor solvent for ionic substances. Among the inorganic compound, all ammonium salt, nitrate, thiocyanate, and iodides are soluble in liquid ammonia. Oxide, hydroxide, carbonate, phosphate, sulfate, and most of the sulfide are insoluble. Most fluorides are insoluble in liquid ammonia, and the solubility among halides increases as F negative is less than Cl negative is less than Br negative is less than I negative. Are quite insoluble in ammonia. Organic compounds such as halogen compound, alcohol, ketone, ester, simple ethers, and phenols, amines, nitro compounds, etc. are readily soluble in ammonia, liquid ammonia. Aromatic hydrocarbons are sparingly soluble. Paraffins and benzene are not soluble. Among the element metal like magnesium, aluminium, zinc, calcium, etc. are only slightly soluble in liquid ammonia. Alkali metals and alkaline earth metals are highly soluble in liquid ammonia. These form very interesting solution and are discussed below. Non-metal like sulfur, potassium, iodine are soluble in liquid ammonia. Solution of alkali metal in liquid ammonia. The most striking property of liquid ammonia is its ability to dissolve alkali metals. The resulting solution are blue and extremely good electrical characters. The important characteristics of alkali metal solution are these are blue in color and the color is independent of the metal dissolved. When the concentration of the metal is increased, the color changes to bronze and show metallic appearance. These solutions are conducting and show strong reducing properties. These solutions are paramagnetic and paramagnetic character decrease with increasing concentration. If the reagent are pure and dry, sodium solution in liquid ammonia are stable and can be preserved for several days. When alkali metal are dissolved in liquid ammonia, they ionize to give metal ions and valence electrons. Na gives us in liquid ammonia Na positive plus electron negative. Both the alkali metal ion and electron become solvated by ammonia molecule. Na positive plus X NH3 gives us the complex ion NaNH3X positive ammoniated cation. And E negative plus Y NH3 gives us a complex E negative NH3Y negative ammoniated electron. The ammonium electrons are responsible for blue color of the solution. The electrical conductance is also due to the ammoniated cations and ammoniated electrons. As the concentration of the solution is increased, the ammoniated cations and electrons associate resulting in decrease of conductivity. Very dilute solution of alkali metal in liquid ammonia are metastable and when catalyzed they undergo decomposition. As the concentration of metal increases, the blue color changes to bronze and finally blue color disappear altogether. On evaporating the alkali metal ammonia solution, alkali metal can be recovered. The strongly reducing character of this solution is due to the presence of the readily available electron. The important application of alkali metal solution in organic chemistry is the reduction of many functional group and unsaturated compounds. As already studied, the liquid ammonia is a thoroughly studied non-aqueous solvent. Some of the advantages and disadvantages as a solvent are given below. Advantages of liquid ammonia as a solvent. The dissolution of alkali metal without chemical reaction is one of the greatest advantages of using liquid ammonia as a solvent. The dissolved alkali metal can be recovered from the solution by evaporation. The alkali metal solution are strong reducing agents, even stronger than hydrogen. Ammonium salt dissolved in liquid ammonia act as amino acid and these find application in preparative chemistry. They can be used to prepare silane, arsine, etc. The tendency for solubilities is less in liquid ammonia than in water. Disadvantages of liquid ammonia solvent. Liquid range for liquid ammonia is from minus 33.3 degrees Celsius to 77.7 degrees Celsius. Therefore, at low temperature or high pressure is necessary while working with liquid ammonia. Liquid ammonia has offensive odor. It requires special technique to use as solvent. Liquid ammonia is hygroscopic in nature. All the reaction to be carried out in sealed tubes. Liquid sulfur dioxide. Liquid sulfur dioxide is a non-protic solvent, aprotic solvent because it does not contain any hydrogen atom. It is also one of the important non-aqueous solvent and widely used in industry. Under normal conditions of temperature and pressure, sulfur dioxide is a gas, but it can be readily liquefied and is easily maintained in the liquid phase. It has a wide range, minus 10 degrees Celsius to 75.5 degrees Celsius, and can be caused you can and can be used as solvent. It can be easily purified by passing the gas through sulfuric acid and through P2O5 to remove traces of water. Its dielectric constant is small, 15.6 degree 15.6 at 0 degrees Celsius. Therefore, is a good solvent for covalent compound. The characteristic physical properties of liquid sulfur dioxide. Freezing point is minus 95.46 degrees Celsius. Boiling point minus 10.2 degrees Celsius. Density is 1.46. Structure of sulfur dioxide molecule. Electron diffraction studies have shown that sulfur dioxide in gaseous phase has the angular structure as shown ahead. The valence bond theory predicts that the aceto molecule is a resonance hybrid of the following two resonating structures. Solubility of compound in liquid sulfur dioxide. Among the inorganic compound, iodide and thiocyanate are most soluble. In case of alkali metal halide, the solubility are in order Mi is greater than Mbr is greater than Mcl is greater than Mf. The Uninegative polyatomic anions such as ClO4 negative, NO3 negative, Bf4 negative, etc. are generally more soluble in liquid SO2. Salt of multi-negative anions such as SO4 2 negative, SO3 2 negative, S2 negative, O2 negative, etc. are practically insoluble. Many of the ammonium, thallium, and mercuric salt are soluble. It is an excellent solvent for covalent compound. Many covalent substances like halogen, interhalogen, phosphorus halides, PCl3, PBr3, etc., oxyhalides of sulfur, phosphorus, etc., and halides are soluble in it. Metal are insoluble in liquid SO2. Among the organic compound, aromatic hydrocarbon and alkenes, pi bonded compound have very high solubility in liquid SO2 in comparison to saturated hydrocarbon. Alkane, pyridine, and quinoline and ethers, halogen derivatives, and acid chloride are also dissolved in liquid SO2. Many compounds dissolve in liquid SO2 due to solvent formation, for example, Ki4SO2. Many donor molecules also form stable solvents with SO2, for example, C2H5N dot SO2, BF3 dot SO2, etc. Autoionization of SO2. Pure SO2 is a poor conductor of electricity, though it is believed to autoionize as 2SO2 gives the equilibrium equation SO2 plus SO3 to negative. The thionyl ion is analogous to the hydronium ion and ammonium ion and sulfite ion, correspond to hydroxyl and amide ions of the aqueous and ammonia system respectively. Reaction in liquid sulfur dioxide. Acid base reaction. Liquid SO2 undergo autoionization. SO2 gives us SO2 positive plus SO3 to negative. According to solvent system concept of acid and base, the compound which are given thionyl ion in solution of SO2 would behave as acid, whereas a compound giving sulfite ions SO3 to negative in liquid SO2 would act as basis. For example, the compounds such as SOCl2, SOBr2, etc. act as acid in liquid SO2. SOCl2 gives us liquid in the presence of liquid SO2. SO2 plus 2Cl negative. SOCl2 is thionyl chloride. SOBr2 thionyl bromide gives us in presence of liquid SO2 SO2 plus 2Br negative. On the other hand, cesium sulfite increases the concentration of sulfite ions and therefore behave as base. CS2SO3 gives us 2CS positive plus SO3 negative. Typical acid base or neutralization reaction in liquid ammonia as SOCl2 plus Ca2SO3 gives us in presence of liquid ammonia 2CSCl plus 2SO2. Amphoteric behavior is shown by zinc and aluminium ions. For example, AlCl3 react with SO3 to negative ions in liquid SO2 to form insoluble aluminium sulfite Al2SO3 thrice. However, if the precipitate is treated with the excess of sulfite, the precipitate redissolves. 2AlCl3 plus 3K2SO3 gives us Al2SO3 thrice plus 6KCl. The reaction is analogous to behavior of Al which thrives in water. AlCl3 plus 3 NaOH gives us H2O, gives us in the presence of H2O AlOH thrice plus 3 NaCl. If some acid SOCl2 is acid to the soluble complex solution, the aluminum sulfide precipitates reprecipitate. If some acid SOCl2 is added to the soluble complex solution, the aluminum sulfide reprecipitate. This reaction is also analogous to the reaction in water. Similarly, salt of zinc shows amphoteric behavior in liquid SO2. ZnCl2 plus K2SO3 gives us ZnSO3 plus 2KCl. Solvolytic reaction. Solvolytic reaction in liquid sulfur dioxide are not as common as they are in other protonic solvents such as NH3. Some reactions are given below. Ammonium acetate is solvolized in liquid SO2. 2CH3C double bond ONH4 plus 2SO2 gives us NH4 cut twice SO3 plus CH3C double bond O cut twice SO. This reaction is analogous to the reaction of ammonium acetate in water. Certain covalent halides such as PCl5, BBr5, UCl6, ASCl5, and WCl6 undergo solvolysis in liquid SO2 in cell tube. PCl5 plus liquid SO2 gives us POCl3 plus SOCl2. PBr5 as in in the presence of liquid sulfur dioxide, POBr3 plus SOBr2. ASCl5 plus SO2 liquid gives us ASOCl3 plus SOCl2. Many binary halides such as SbCl3, SbCl5, SiCl4, SnCl4, etc. do not have undergo solvolysis in liquid sulfur dioxide. The formation of solvate addition compound with solvent is known as typical. Typical example of solvates are NaI.4S2O, SO2, RBI.4SO2, KBr.4SO2, etc. Precipitation reaction. A large number of precipitation reactions can be carried out in liquid sulfur dioxide due to selective solubilities of compounds. The precipitation of several insoluble compounds in liquid sulfur dioxide can be carried out by treating them with soluble compounds in sulfur dioxide. Some of the reactions are SbCl3 plus 3 Li in the presence of liquid sulfur dioxide, SbI3 plus 3 LiCl. PbF2 plus Li2SO4 in presence of liquid sulfur dioxide, PbSO4 plus 2 LiF. Thionyl derivative can be easily prepared in liquid SO2 by action of thionyl chloride, 2Ki plus SOCl2 in the presence of liquid sulfur dioxide, 2KCl plus SOI2. Fourth is complex formation reaction. A large number of complex ion formation in liquid sulfur dioxide have been reported. For example, solubility of iodine in liquid sulfur dioxide is greatly increased by the addition of potassium or rubidium iodide. This is due to the formation of the complex Ki3 or RBI3. Ki plus I2 in the presence of liquid sulfur dioxide gives us Ki3. RBI plus I2 in presence of liquid SO2 gives us RBI3. Similarly, the increase in the solubility of cadmium iodide and mercuric iodide in liquid sulfur dioxide is attributed to the formation of the complexes. CdI2 plus 2Ki is in the presence of liquid SO2, K2 CdI4. AlCl3 react with SO3 2 negative ions to form a precipitate of Al2SO3 thrice, which redissolved in excess of SO3 2 negative ions, forming the complex ion AlSO3 thrice. Organic reactions. A large number of organic reactions have been carried out in liquid sulfur dioxide because organic compounds are soluble in it and it is a relatively inert solvent. Some common examples are sulfonation of aromatic hydrocarbon by sulfur trioxide or chlorosulfuric acid. C6H6 plus SO3 gives us liquid SO2, C6H5SO3H. Liquid SO2 has also been used as a solvent for Friedel-Crafts type reactions. In these type reactions, AlCl3 is used as a catalyst which is highly soluble in liquid SO2. C6H6 plus TC5H11Cl. in presence of liquid SO2 AlCl3, TC5H11 C6H5 plus HCl. It is also used as a solvent for addition and substitution of bromine reaction. Phenol is taken plus Br2 in the presence of liquid SO2 gives us bromine plus HBr. Not bromine, bromophenol is obtained. Sulfur dioxide of crystallization. These reactions are also called solvation reactions, like water and ammonia. Salt having sulfur dioxide of crystallization have also been observed. Some examples are Ni.4SO2, Ki.4SO2, Lii.2SO2, etc. These are formed with a highly soluble salt and are analogous to hydrate. 7th, redox reaction. Though gaseous sulfur dioxide behaving both as oxidizing as reducing agent, liquid sulfur dioxide does not show any marked reducing or oxidizing tendency. It simply acts as a medium for certain redox reaction. For example, iodine is liberated from Ki in the presence of SbCl5 in liquid sulfur dioxide. 2 Ki plus 2 FeCl3 gives us 2 FeCl2 plus 2 KCl plus I2. 6 Ki plus SbCl5 gives us 2 K3 SbCl6 plus SbCl3 plus 3I2. Some special features of liquid SO2 as a solvent. Liquid sulfur dioxide possesses some special advantages over other solvent as a reaction medium. Some of these are: first is it has low boiling point and this allow it easy evaporation and therefore removal from the reaction mixture. Second, it has low melting point and therefore it allows reaction to be carried out at low temperature. Third, liquid SO2 is an inert solvent. Fourth, it has unusual solvating power for both covalent and electrovalent compound. Fifth, it is a better medium for covalent compound like hydrocarbons and is used for the purification of some petroleum products. Sixth, it is used as a diluent for the superacid medium. HSO3F HSO3F is bonded with SPF5, which help in reducing its viscosity without affecting its acidity. Thank you.